Hello guys, welcome to Deep Codes, and in today's video we will discuss LeetCode question 226 that says invert binary tree. So here you are given one binary tree, you are given the root of the binary tree and you need to invert the tree and return its root. Okay, so here what does the invert word mean? Invert the binary, what does that mean? So let us understand that with this first example. So here you are given this binary tree and you need to invert it. So yeah, as you see that this root node 4 has left child 2 and right child 7. So in inverted binary tree, you just swap this child. That means that the right child becomes the left and left becomes the right. Simple as it is. See, the 7 becomes the left child and 2 becomes the right child. Now again for the node 7, its left child was 6 and right child was 9. But we swap it. We swap so that the left child of 7 becomes 9 and right child becomes 6. Similarly, the left child becomes 3 and right child becomes 1 after inverting, or you can swapping. We are simply swapping the left child as well as the right child for each node, as you can see here from this example. Got it? Now here 2 is our root node and 1 is the left child, 3 is the right child. So what does invert mean? Invert means to swap the left and right child. Thus unswapping, the left child became 3 and the right child became 1. In the third example, we have nothing in the root, so we return null or empty. Correct? Now let's take a look at this example. So suppose you have this type of example and you need to invert it. So tell me, the root remain as it is, correct? Now what we now in order to invert this tree, what we are doing? We are simply doing swapping of the left child with the right child, correct? So here comes 2 and here comes 1. Okay, we just swap them. Now internally for 2 also we are swapping the left and right child. So the 2's left child will become 6 and its right child will become 5 and 1's left child will become 4 and here it will be 3. Okay, now for 3 also we need to swap. So here it would become 8 and here it would be 7. For 4, its left child was 9 but it's now its right child will become 9. Okay, everything here would be null. This would be also null, 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 null. So yeah, this is how we invert the binary tree. Okay, this is how the inverted binary tree looks like. So now I hope you guys understood the question. It is simple as it is, but now in order to invert this, how what you can do? See, as you can see here that we are just traversing all the nodes and doing some operation. Okay, for each root node or each parent node we are performing some operation on the child node. Here we are swapping that. So in order to traverse all the nodes, what do we need to do? We need to do something like BFS or DFS traversal. Okay, simple. Like we need to do some type of traversal in order to invert this tree. Okay, and what another thing we are doing is for each root node, like that for each root, what we do, swap left and right child. This is the only thing that we are doing to invert the binary tree. We are swapping the left child with the right child and the right child with the left child. We are just swapping them, left and right child. Okay, yeah, this is our approach. We will either do BFS or DFS traversal and we will swap each child. Correct. Now let's move on to the coding part where we will look at how we are actually performing this. So first let me show you the DFS approach. So yes, this is the DFS approach. See guys, as you can see here that here these two lines, these three lines actually, here what we are doing, we are performing swap of left child with the right child and right child with the left child, correct? And then we are again doing DFS on the left child and then DFS on the right child. Similarly similarly to perform the swaps on its children. Okay, so yeah, let me show you by drawing this, that if you have 2 3 4, if you have something like this. Okay, so initially it will check if the root is empty. No, it is not empty for the root 0. So for the root 0, what we are doing, we are swapping its left and right child. So it will be 2 and 1 here. Okay, this would be your answer. Now what we are doing, we are traversing for its left, so our left is 2. Okay, so now we are traversing again. Now what is the root? Root is 2 for this, and then again we are checking if the root is null. No, root is not null. Then we are swapping left and right. So yeah, but both is null, left and right, so it doesn't make sense. Okay, Now you traverse again, so this is second time traversal with, but here the root is null, like this is null and this is also null, so either you do both of this, it is null. So in that case we return and traverse its right child. Okay, right child of node 0. So this right child of the node 0 has two children, 3 and 4, so we will swap them. Okay, 4 and 3. Whenever we traverse the solve function, whenever the solve function we call for 1, at that time we will traverse the node 3 and node 4 as per this. Correct? So yeah, this is how DFS traversal works, that each time we are traversing for some not null root, then we are just swapping its nodes. Correct? Left and child nodes, left and child nodes, and in the end we are simply returning no root node. So I hope you guys understood the DFS approach. Now let us also discuss the BFS approach. BFS approach is also similar as to DFS. So here, as we know, in the BFS we use one cube, and initially we push the root, right, and then for every root which that is present in the front of the cube, we just store it in the current, and yeah, we swap the left child and the right child of the current, as you can see here. And we check that if the current left is not empty, then we push to the queue, and if the current right is not empty, then we push to the queue. Correct? So yeah, and in the end we return. So yeah, now talking about the time and space complexity. So the time complexity here would be big O of n, right, as we are traversing all the nodes present in the tree. So the time complexity here, it would be big O of n. And for the space complexity, it would be also almost too big of n in the worst cases. And this is for both the approach, DFS as well as BFS. Regardless of approach, it would be the same. Yeah, the time complexity is big of n as we are traversing all the n nodes, and the space complexity is big of n. See, it is somewhere big of h. H is the height of the tree, but in the worst situation, when all the nodes are present in the queue or in the recursive stack of DFS, then in that case our space complexity would be big of n. So yeah, in the worst case it is big of n, and is the time complexity is also big of n. So I hope you guys understood the question, the approach part, as well as the coding for both the approaches. And if you have still doubts, then do let me know in the comment section. Also do check the community section of this channel where you will find the job posting. So I'm regularly updating that section as well. So yeah, that's all for this video from my side today. Make sure you like this video and subscribe to our channel. Thank you.